Hello, students. So let us continue with Chapter 7 Systems of Particles and Rotational Motion, Part 6. So today we will study about equilibrium of a rigid body. So, what is a rigid body? A rigid body has a perfectly definite and unchanging shape and the types of equilibrium a rigid body has. We will study about that. So we are going to discuss about mechanical equilibrium. So a rigid body is in mechanical equilibrium if both its linear momentum and angular momentum are not changing with time. Now let us take it one by one. If a rigid body has its linear momentum changing with time, we represent it as d by dt of p, dp by dt, which is equal to force. So here we know linear momentum is not changing with time. That means force is zero. The total forces acting on a body will be zero. Then the rigid body is said to be in mechanical equilibrium. That is the first part. The second part is its angular momentum also should not change with time. So what do we get when angular momentum changes with time? When it changes with time, we get torque. So if it does not change with time, torque will be zero. So let us see what is represented here. The total force, that is the vector sum of the forces acting on the rigid body, is zero. Sigma I equal to 1 to n Fi equal to 0. Then the body is said to be in translational equilibrium. Force is a quantity which is associated with linear motion or translational motion. So when force is zero, the body is said to be in translational equilibrium. Same way for angular momentum. If it does not change with time, then the total torque, that is the vector sum of all the torque acting on the rigid body, is zero, or we can say sigma I equal to 1 to n, tau I equal to 0. Then the body is said to be in rotational equilibrium. So the two types of equilibrium which comes under mechanical equilibrium are translational equilibrium and rotational equilibrium. Now if you put it in a formula form for translational equilibrium, sigma I equal to 1 to n, Fi equal to 0. And if you break Fi into its components along the x-axis, y-axis and z-axis, we can write it as sigma I equal to 1 to n Fix equal to 0, sigma I equal to 1 to n Fiy equal to 0, and sigma I equal to 1 to n Fiz is equal to 0. All these are conditions for translational equilibrium of a rigid body. So there are three components here, independent conditions here. Similarly, for rotational equilibrium, sigma I equal to 1 to n, tau I equal to 0. So here also the rotational factor tau can be split into its components along the x-axis, y-axis and z-axis. So altogether, these equations denote 6 independent conditions to be satisfied for mechanical equilibrium. Now suppose the forces acting on a rigid body are coplanar. What are coplanar forces? Coplanar forces are forces which will act on a body only in one plane. And what is a plane? It has two axes, two coordinates, maybe xy plane or yz plane or xz plane. So there will be only two coordinates. Therefore, conditions for translational equilibrium will have only two conditions. The sum of the components of the forces along any two perpendicular axes in the plane must be 0. So there will be only two coordinates here. And the conditions will be for coplanar forces acting on a rigid body, the sum of the components of the forces along any two perpendicular axes in the plane must be 0. Now, what about rotational? How will rotational equilibrium be satisfied? So, if the first two conditions for translational equilibrium are in one plane, then for rotational equilibrium, the torque will be in a perpendicular plane. For example, if translational equilibrium or the coplanar forces act along the xy plane, then for rotational equilibrium, the torque will act in the z axis, along the z axis. There will be only one condition satisfied here. So when coplanar forces act on a rigid body, there will be only three conditions for mechanical equilibrium. Two conditions are for translational equilibrium and one condition will be for rotational equilibrium. Next, we are going to consider or discuss the conditions of equilibrium of a particle. So till now we were discussing conditions of equilibrium of a rigid body. Now we are proceeding to discuss the conditions of equilibrium of a particle. You know what is a particle? A particle is represented as a point mass. It has no size. A point. So it doesn't have a surface, it is just a point. So when all the forces act on the point, then the forces must be concurrent. And when you consider concurrent forces, you will have to consider all the three axes. So a point mass cannot rotate. So then there will not be any rotational equilibrium. So conditions of rotational motion does not apply to a particle. Only conditions of translational equilibrium apply. Thus, for equilibrium of a particle, the vector sum of all the forces on it must be 0 and the forces will be along all three axes. Since all these forces act on a single particle, the forces are concurrent. For example, look at the concurrent forces. At the point O, we have the particle and all the forces are acting on the particle at the point O, so they are concurrent forces. Concurrent forces are forces which act at a point, which meet at a point. Coplanar forces are all parallel forces and they will not meet at a point, they act in one plane. Next is partial equilibrium. A body may be in partial equilibrium. It may be in translational equilibrium and not in rotational equilibrium. Or it may be in rotational equilibrium and not in translational equilibrium. Let us study the diagram below. So here we have a light rod AB and it is clamped or it is pivoted at the point C. So you can see two equal forces acting in the downward direction from A and B. And they are equidistant from the center, represented by small letter A. So when two forces, you can see the first force at A will be acting in the anti-clockwise direction and the other one will be acting in the clockwise direction. So net moment on the rod is 0. What is moment? Moment is force multiplied with AC, the distance between the force and the perpendicular distance AC. And the other moment on the right side will be F into BC. Net moment on the rod is 0. So the system is in rotational equilibrium. It will not rotate, but not in translational equilibrium. Look at this diagram. You have two forces which are equal but acting in opposite directions. So the moment on the left side will be F into AC. It will be in the anti-clockwise direction. And the moment on the right side also will be F into BC, but it will also be in the anti-clockwise direction. So it will make the rod rotate in the anti-clockwise direction. There is a turning effect for this body. So it is not in rotational equilibrium. It is rotating. So it is not in rotational equilibrium. It will be in translational equilibrium. I hope you have understood that. Now coming back again to torque, you can see as represented by the diagram, that is the turning of a wheel and the applied force. Applied force is in one direction here, and the distance from the center, from the axis of rotation to the applied force is R. Now F and R are seen to be in one plane, whereas torque or the turning effect is in a perpendicular plane. And of course, you already know torque is moment of force, which causes turning effect to a rigid body. So let us see what is it is represented here. It is represented again as F in this direction, R. So we have angle between them is theta from R. Between R and F is theta. So torque is given by R vector cross F vector, which when expanded will give RF sine theta. And torque will always act in a perpendicular plane. Another example of torque, a pair of forces. You can see the opening of a lid with the fingers. The thumb moves backwards, but the other fingers move forward. So we have equal forces, two equal forces in opposite directions. They constitute a couple. You have studied about couple and torque in lower classes. So as a result, the lid rotates. So there will be a couple produces rotation without translation. There will not be any linear motion. There will only be rotational motion. Another example for couple and torque is the Earth's magnetic field exerting equal and opposite forces on the poles of a compass needle. Poles of a compass needle. So you can see as represented by the arrow marks. These two forces form a couple and cause the compass needle to rotate. Next, we are going to study about principle of moments. So here the diagram is slightly different. We have a light rod AB as you can see, and it is pivoted at the point O. So the distance from A to O is represented as D1 and the distance from B to O is represented as D2. So you can see there is a force F1 at A and a force F2 at B. So if F1 is greater, then A tends to rotate in the anti-clockwise direction. But if F2 is greater, then the rod tends to rotate in the clockwise direction. We take anti-clockwise direction as positive and clockwise direction rotation as negative. So the point at which the light rod is pivoted is called the fulcrum. So the point O here is called the fulcrum. So the lever is a system in mechanical equilibrium. So here, how do we balance? How do we keep this light rod in equilibrium? What is the condition? So if it should be in translational equilibrium, then the upward force must be equal to the downward force. The upward force is R. You can see the reaction R. Whereas the downward forces are F1 plus F2. Both are acting in the downward direction. So if the reaction R is equal to F1 plus F2, then the body is in translational equilibrium. Or we can write R minus F1 minus F2 equal to 0. What about rotational equilibrium? The anti-clockwise moment must be equal to clockwise moment. What is the anti-clockwise moment here? It is on the left side. So F1 into AO or F1 into D1 is the anti-clockwise moment. As I told you, anti-clockwise moment is taken as positive. What is the clockwise moment here? It is F2 into D2. So we have the total moment will be D1 F1 minus D2 F2 is equal to 0. Then the body will be in rotational equilibrium. So this is called the principle of moments. Now, in the case of lever force, F1 is usually called some weight to be lifted. If this is applied, an application of this principle of moments, F1 is usually some weight to be lifted. It is called the load, and its distance from the fulcrum D1 is called the load arm. Whereas force F2 is the effort we apply to lift the load. So distance D2 of the effort from the fulcrum is the effort arm. So when we try to lift a load, normally effort must be the effort we should apply minimum effort. So F2 must be less and F1 must be more for the lever to be of good advantage. So we have a formula according to the principle of moments D1 F1 equal to D2 F2. So load arm into load equal to effort arm into effort. Now the ratio F1 by F2 is called the mechanical advantage. So F1 by F2, and at the same time it will be equal to D2 by D1. Accordingly, we have classified levers into three types. Class 1, if you look at class 1 lever, you can see as shown in the diagram here, class 1 lever, the load is at this end, so that is F1, and the fulcrum is in the center, and the force or the effort is on the right side. So if you look at the arms, D1 will be less. That means load to fulcrum D1 and force to fulcrum is D2. So as per the diagram, you can see D2 is greater than D1. So mechanical advantage will be high. What about class 2? And the examples and their applications are hammer, a claw hammer and pliers. Look at the claw hammer. We can see the fulcrum, the stationary point is at F. On the left side, we have the load. We are trying to pull a nail from a surface. And what is the effort we do? We use the handle of the hammer and pull it to the right side. That is the effort. And the nail comes out. So this is an example of class 1 levers. Look at the second example, pliers. You can see at the tip, we keep maybe a wire to be broken, or we have to cut a wire or cut something hard. That is the load. The fulcrum is in the center. And the effort, we use our force on the handles. So fulcrum in the center, load on the left side, effort on the right side. This is class 1 and mechanical advantage will be high, greater than 1. What about class 2? In class 2, we can see the fulcrum is at one end. Left load is in the center and force or effort at the right end. Here also, if you look at the distance from load to fulcrum is D1 and from force to fulcrum is D2. Obviously, D2 is greater than D1. Therefore, mechanical advantage will be high. And the examples are a wheelbarrow and a nutcracker. Look at the wheelbarrow. You can see there is one wheel, and at the wheel is the fulcrum. The center of the wheel is the stationary point where it is the fulcrum. The load will be inside the container part of that wheelbarrow. So heavy load we can carry just by pushing, giving an effort at the right side at E. So you can lift the effort part. If you lift, then you can carry that heavy load. So here the mechanical advantage is very high. Look at nutcracker. The fulcrum is at the left end. The nut to be cracked is in the center, that is the load, and the two handles we will press, that is the effort. Here also a nut can be broken. So mechanical advantage is high for class 1 and class 2. Let us observe class 3. So in class 3, fulcrum is at the left end, but force is in the middle and load is in the right side. So here force to fulcrum is D2 and load to fulcrum is D1. So here D1 is greater than D2. So this type of levers are used to pick up things, not to carry heavy loads. For example, the human arm. You can see the elbow joint is the fulcrum. The effort is done by the muscular part of the arm, and we can see we are picking up a book or a purse or something which is not too heavy. Mechanical advantage is less here because D1 is greater than D2. Look at the sugar tongs, just 1 cube of sugar, it doesn't weigh much. So just to pick up an ice cube or a sugar cube, you can use these type of tongs. So fulcrum is at the left end, effort is in the middle, and load. This load is not very heavy. So mechanical advantage will be less than 1. So if it is written, you can see how mechanical advantage varies. In class 1, effort arm greater than load arm, D2 greater than D1, mechanical advantage will be greater than 1. Class 2, effort arm greater than load arm, D2 greater than D1, mechanical advantage greater than 1. And in class 3, effort arm is less than load arm, so D1 is greater than D2, so mechanical advantage will be less than 1. Okay, thank you students. We will continue in the next session.